All right, this is an alternate assignment since cohort A apparently does not come to class 2 days a week due to weather or holidays or who knows what from PLSD scheduling. At any rate, we do need to go over some things since we're already behind cohort B. These are things I did in class, so I'm going to make this into a lecture and an ed puzzle. You should have already gotten a new version of the formula sheet. Not that it's any different, but just something to look at. So in the wave formulas, which are sort of in the upper right-hand corner of that side of the formula sheet, the first 5 deal with optics and things that are in chapter 18. So this is a slightly rearranged version of the one they show. They show lambda, which is wavelength, is equal to velocity over frequency. I've seen it traditionally written more like this. W2 is the relationship between index of refraction, speed of light, and speed in a substance of different optical density. So C stands for speed of light in a vacuum. That's 3 times 10 to the 8th or 300 million meters per second. V is the velocity of an object in something that is more optically dense than a vacuum. N is that index of refraction, which is simply the ratio of those two things. So this N can't be less than 1 for our purposes, because things always slow down as they get into something more optically dense. They don't speed up. Now, air is pretty low density, so it's like 1.001, I think. Water has an index of refraction or an optical density of about 1.33. Certain types of glass about 1.50. Diamonds around 2.42. And this is Snell's law, or the formula we use to think about the index of refraction. And this N1 is the index of refraction in the first material that you're going from, the angle with respect to the perpendicular line or normal compared to the angle material you're coming from. This is the index of refraction of material 2 and the sign of the angle in the second substance. So almost always you'll know 3 of these 4 things, or maybe you'll know something up here to get one of those other things and then solve. You do need to be careful because your calculator needs to be in degree mode to solve these properly. Sometimes you're going to take inverse signs when we solve problems with that. W4 is a general equation for lenses and mirrors, so it's really quite important. So 1 over the image distance plus 1 over the object distance equals 1 over the focal length. In this particular case, your formula sheet shows this different. It shows it as SI and SO. I'm not sure why they chose to use S's for position in those places, but they did. All these are measured from the optical device, so from the surface of a mirror or lens. This can be algebraically rearranged into this to solve for DI. I guess it could also be algebraically rearranged to solve for DO if you knew the DI and you'd put DI here and DI here. But I tend to use this. It's not written on your formula sheet like that, but it's useful algebraic rearrangement. W5 deals with the magnification, and that is simply the ratio of height of the image over height of the object, which is also equal to the distance of the image over the distance of the object. Traditionally, images that were right side up were called, had a positive magnification, and those upside down had a negative magnification. But notice on your formula sheet, these all have absolute value bars. So that's kind of the first part of this, going over those formulas. So it's important to note that an object has rays of light reflecting off it in all different directions. And so what we tend to do with ray diagrams and with some of the calculations, and actually I'll maybe put this over here so we can refer to it if needed. What we tend to do is we tend to only draw 2 or 3 rays, which are going to allow us to make predictions about where or if an image is going to form and what kind of image it's going to be. So there's all sorts of other rays there, but there's rules for a few of them that are going to make our lives a lot easier. So I want you to be able to know how to draw ray diagrams, but also to calculate them. So this sheet, which everybody should have, is asking you to both do some diagrams with drawings and calculating. So for cohort A, I'm going to ask you that you probably do the calculations. I don't know if you can do the drawings that well without a drawing compass, And if you're unsure what a drawing compass is, they look something like this. And up here, there are numbers. On one side, it's inches. The other side, it's centimeters. And that can tell you, like, if you put this little lever or this marker here at, say, 8, these will be 8 centimeters apart. So that'll be the radius of a circle. So we're talking about optical devices like mirrors and lenses. We think of circular or spherical mirrors and lenses. So the main reason we think about that is they tend to be cheap. Parabolic mirrors and lenses are actually better at focusing things. So because spherical mirrors and lenses aren't as good, they don't form as nice or as tight an image. And that's actually something called spherical aberration, meaning when you get an object that's just a little bit blurry or an image that's a little bit blurry because the mirror is not shaped like a parabola. At any rate, here's how we're going to start drawing things. Let's see if I can get a good marker here. If we have a plane mirror that's flat, what we end up having happen is, let's say we have an object over here, and let's say it's a Christmas tree. So something like that. So light rays come, and we're going to say that light is coming from the left and going to be reflected back to my left. So if I have something like that, if I have a ray of light that goes straight in, it would reflect straight back. If I have a ray of light that goes in like this, remembering our law of reflection, we have a certain angle here like this, but actually bounce out at the same angle. So whatever this angle is of incidence, this angle of reflection, and doesn't look like it because I didn't draw it very well, should be the same. So if this is 30 degrees, that'd be 30 degrees. If this is 40 degrees, that would be 40 degrees. So what ends up happening, and I really wish I drew this a little bit better. Maybe I can try. That looks a little bit better. Is your brain thinks this reflected ray of light comes from back here. Thinks it comes back in a straight line. Your brain would think that this ray of light, which goes straight back parallel, comes back from there. So those two rays are behind the mirror. They don't really cross because the light bounces back to the left. But your brain thinks they cross back here. So you actually would see an upright image of the Christmas tree, equidistant behind the mirror as this is in front of the mirror. So if this were, say, 2.5 meters, that would be 2.5 meters. It'd appear like you'd think, hey, that's a tree that's 5 meters away. So that's how a plane mirror works. We're going to get to curved mirrors because they're a lot more interesting, though. So I'm going to erase this. If I have a curved mirror and it's curving like this, curving inward, that is a concave mirror. So and that's assuming, again, light is coming from the left and this is a reflective surface. And over here, this side, it was not reflective. We're not thinking about the light over there right now. At any rate, we would think of this as a giant circle. And the center of that circle, it's fantastic, would be somewhere like this. I'm going to draw a line straight across in the middle. That's called an optical axis. And all that is for reference to us to know where something is above or below the optical axis. So if this is the center of curvature, that is sometimes called C, or could be called R because it's the radius. For spherical mirrors, because of how the law of reflection works, our focal point would be here, halfway between the surface and this. So if on the sheet you're told that you have a radius of, say, 10 centimeters, that means your focal length is 5 centimeters. Now, it's important for you to understand that images don't always form at the focal point. In fact, they very rarely form close to the focal point. But we can use the focal point to help us draw some things. So I'm going to just call this R here. So I'm going to draw several different situations. If we wanted to calculate things out, we would end up using the formula we talked about before. 1 over di plus 1 over do plus 1 over f. Or we could think of it as di plus do times f for do minus f. So I may end up doing some of those calculations in a little bit. All right. So with something like this, let's say I've got an object, and I'm going to draw an object as an arrow. That's how they're often drawn, only because we tend to draw the light rays passing over the tippy top of that arrow, or it could be like the Christmas tree I drew earlier, just so that we know what's upright and what's inverted. Again, remember, in reality, light rays go all different angles and in all different directions. Okay, so thinking about that, let's say that this radius of curvature is 20 centimeters. And this focal length is 10 centimeters. And now let's say I'm going to have an object here that's going to be 40 centimeters away. I have no idea what these really are. So that's my object. It's an arrow. It's going straight. It's upright. So I'm going to draw a couple of crucial rays. There's 2 or 3 rays we could draw. So one of which is, if we have a ray of light passing from behind over the top of this arrow, it would go straight in, parallel to the optical axis. If you have rays of light that all come in parallel to the optical axis, they're all going to reflect through the focal point. So you would get a tiny, tiny image just at or just outside the focal point. So something like that. So this is the incident ray, and that's the reflected ray. So that's one common ray to draw. The second most common ray to draw is a ray that comes in through the focal point. I'll see if I can do that. And it reflects back parallel to the optical axis. So it's kind of like the flip-flop of that first one. So something like this. So the question is, do we get an image of any sort? And we do. In fact, we get what's called a real image because these 2 reflected rays of light really cross at that location. And if you notice, they're below the optical axis. So I'm going to draw that image is upside down. So real images are inverted, and the light rays that are reflected really do cross each other. Okay, and it happens right there. So there's another couple places that you could draw, another couple light rays you could draw. You could draw one coming from the tippy top of this, hitting at this point, and it'll reflect back down at the exact same angle. That light ray should also cross through here. The other thing you could do is draw a light ray coming through the center of curvature. It'll reflect straight back because this radius is at the center of curvature. So that means any ray that passes from here to the surface of the mirror ends up hitting the mirror perpendicularly, and it reflects back the exact same direction. So it would be something like this. Oh, I drew that really nice. So that comes back this way. Again, all 3 of those rays now would end up crossing right there. Now normally that gets too messy. So if I can, I tend to only draw the first ray I drew, going in parallel and reflecting back through the focal point, and then the second one going through the focal point and reflecting back straight. So now the question is how can I calculate where that focal length or where that image distance is? If I go over here, I'm going to use this version of the formula. I could use this. I could say 1 over di plus 1 over 40 equals 1 over 10. Fractions are a pain in the butt because then when I solve for things, I end up getting an answer, but that's not the object distance, it's 1 over the object, or well, it's not the image distance, it's 1 over the image distance. Whereas this is a little bit easier, I think. So here I'm going to have di. My object distance is 40 centimeters. My focal length is 10 centimeters. My object distance is 40. My focal length is 10. So I end up with 400 centimeters squared over 30 centimeters. Centimeters squared divided by centimeters gives me centimeters as my unit. And in this particular case, that image distance is going to be 13.3 centimeters. Now that's a positive number. That's kind of important. So if we have a positive image distance, that actually means that we have a real image, which we do, and it tells us again that that image would be inverted. So this is probably my best diagram ever. The rest of them are not going to look this good. So because this really does look like it's about 13 centimeters out. So we want you to be able to do the diagrams and definitely do the calculations. They normally don't agree this nicely. So next I'm going to do another example. Same type of mirror, same focal length, but I'm going to move the image in, or the object in closer. I'm going to try to simplify it and only draw 2 light rays at this point. So there's my optical axis again. I wish I had kept my, I guess that's the focal point. Somewhere like this was the center of curvature of the radius. 10 centimeters, 20 centimeters. So now let's say I've got this object and I've moved it into this point, 20 centimeters away. So I'll draw this ray still, going straight in, reflecting back through here. I'll draw this ray going through the focal point, reflecting back parallel to the optical axis. And notice that these 2 rays cross here. So once again, the 2 reflected rays really cross, so I have a real image. And if you notice, it's bigger and the image is further away. So as the object got closer, the image got further away. If I was to do that calculation, I could say here, my image distance (20 times 10 to the focal length over 20 minus 10 is equal to 20 centimeters. So it should be at the same location as the object, just inverted and below. And it's pretty close. All right, so let's do this again. Try to mark that down. Not bad. Okay. So again, R, F, 10 centimeters, 20 centimeters. If I move this in here, I'm going to have the same thing that I've drawn the last 2 times. My image will be bigger and further away. But something odd happens if I end up putting the image at the focal point. I put it here. Oh, that was black before. No, it wasn't. I don't know. So something like that. This ray I can draw the same as I did before. Doesn't look very good. But I can't draw a ray from here through the focal point anymore. It's just not going to work. But what I can do is I can draw a ray from the center, passing over the top, and something like that. When I do that, it's going to reflect straight back. And these ideally should be parallel to each other. So the rays will never cross. So the interesting thing is, if you recall, when we have rays coming in all parallel, they end up crossing at the focal point. But when we have an object at the focal point, the light rays never cross. And so, in fact, you don't produce an image. So I have di equals, this is at 10 centimeters. Focal length is 10 centimeters. 10 minus 10 equals 100 centimeters squared over 0. Math does not like that. You can't divide by 0 that's undefined, and in fact we have no image formed in this particular case. All right, so I'm going to do one other thing with this type of mirror. I'm going to move it and that's pretty good. Maybe there. I'm going to move it so that my object is inside the focal point. So something like this. So let's say that this is at 6 centimeters for my object. So draw the rays again. The first ray I can draw like this. It goes in parallel to the optical axis and reflects back through the focal point, kind of like we've seen before. Again, didn't do a great job with this focal point. The second one, I can't pass through the focal point after the light ray comes from here, but I can have the light as if it is coming from the focal point. So I can have it go up like this, hit the mirror, and it's going to reflect back straight or parallel to the optical axis. Again, I could have a light ray coming in here from the center of curvature and also going straight back. At any rate, those two light rays that are reflected don't really cross each other. And so I don't get a real image. But if your brain has an eyeball over here, like mine does right now, these light rays that are reflected back from this curved mirror, our brain thinks that they come from back here. So it thinks that they continue straight, the reflected rays. So they don't really cross, but our brain thinks that they cross behind or inside the mirror. We see a large image that is upright. So this is a virtual image. Do the light rays really cross? No, but our brain thinks they do, and that's why we call it a virtual image. So this is something you can see inside a mirror or lens, but you can't project onto a screen. So how would we calculate that? Well, if I go and use this formula again, I would say my di is equal to do, that's 6 centimeters, times my focal length, that's 10 centimeters, over do, 6 centimeters, minus the focal length, that's 10 centimeters. So I get 60 over negative 4. That's negative 15 centimeters. Well, that's interesting. Well, what does the negative mean? The negative is what tells us we have a virtual image. So whenever I get an image distance that's negative, it says I've got an upright image, it's a virtual image, and it's inside the mirror surface itself. In this case, it's going to be pretty big. And again, this should be further away than this is. The scale's not that great. Okay, we've got one more example to do, and this is with, all these were with a concave mirror. We're going to do one with a convex mirror. So in class, I've had these mirrors for a while. And so what you should be able to see is, hey, if you're pretty far away, this should give you an upside down image. That upside down tells us we could get a real image from that. If we move it close, at some point, it should cause things to be right side up. I don't know if that's going to work in a mirror of a lens, reflected, reverse images, stuff like that. So who knows? A convex mirror, though, is different. Convex mirror curves, I guess I would call it curving outward, instead of inward. And what we get is always get upright images, and they're always smaller than we end up seeing in real life. So the reduced images. And because they're upright, they're always virtual images as well. So let me go ahead and draw that. So while a concave mirror is called a converging mirror, because the light rays tend to come together or converge, a convex mirror is called a diverging mirror, because the light rays spread apart. So again, we'll still imagine the light coming from the left, but now it's going to be our mirror surface is going to be curved like this. So draw the optical axis again. Here, this radius or center curvature is behind the mirror surface, and the focal point is behind the mirror surface. Now the key thing about this is, since these are diverging mirrors, and this focal length and radius is behind the surface, we're going to think of those as negative distances. So let's say that's negative 20 centimeters, negative 10 centimeters. That's actually going to be important for our mathematics. So the negative matter. Now let's say I'm over here and I've got an object, something like that. I don't know how far that is. Let's say it's, I could move it like this. So let's say that that object distance is also 20 centimeters. So what I'll do is I'll draw a couple rays. Here's how I do that. The first one, I'll draw parallel to the optical axis. That's similar to what we've done several times before. Now I can't go into the mirror, but what we can do is we can think of it as if it would reflect from the focal point. And it'll go out like that. We could also have a ray of light come in as if it's going to the focal point, like this. But in fact, it's going to reflect back parallel to the optical axis. And your brain thinks that that's where those two rays of light actually cross. You could also do a third ray of light coming from here, going directly to this radius or center of curvature and coming straight back. It would actually have its virtual ray cross at that same location. So when I look at where these virtual rays cross, again, they don't really cross, and the two reflected rays don't ever really cross, but our brain thinks they do inside the mirror. So once again, we've got an upright virtual image. But in this case, a convex lens will always have a reduced image. So let's go ahead and calculate that. If I use the version of the formula that I've had before, which is di equals do times f over do minus f, my object distance is 20 centimeters. My focal length is negative 10 centimeters. That's important. Do minus f, 20, minus a negative 10 centimeters. So subtracting a negative is the same as adding. So what we end up getting is that this is negative 200 centimeters squared. 20 plus 10 is plus 30 centimeters. And I think that's negative 6.67. And that is our object or image distance. So that seems about right, because if that's negative 10 centimeters, that's negative 6.67. In fact, For a virtual or for a convex mirror, your image should always appear between the focal point and the surface. When you have a concave mirror, if you have a real image, it's always going to form just outside the focal point to a point that's quite far away. You'll never get an image in the region, real image in this region close to the surface. At any rate, those are a lot of examples. It's 30 minutes, sorry about that, but that's kind of what we were going to do in class. So I'll put an Edpuzzle up.